Hello everyone, welcome to ECE 6520, lecture number 9. Today we're going to go over our homework 1. Okay, so we're gonna go over our homework one by one. So in homework we totally have 16 or 17 questions. So they are 2.1 to 2.7 and 2.9, 2.12 and 2.14 to 2.16, 2.19, 2.20, 2.25 and 2.29. Okay, so let's go over them one by one. Okay, first let's take a look at 2.1. So first of all, for information theory, in lots of cases it is hard to find intuition from the beginning, right? So yeah, sometimes it's possible, sometimes it's hard, right? So basically sometimes we need to try all the possible cases, and after the solution then we need to think back about why it is the case, right? So this happens pretty frequently. Okay, so let's get started. So for 2.1 is a coin flips. So in this problem we have a coin and it's flipped until the first head occurs, right? And then let the random variable denote the number of flips required, right? And the first question is that it asks us to compute the entropy of X. Okay, so let's see how we solve this problem. Okay, so in this one and for part A, so what we get is that so we have a random variable X, so that is the number of flips required until the first head, right? Okay, and we can see that, for example, if let's say the probability X is 1, so it means that the first one is head, right? So maybe let's denote the probability, right? Let's denote the P is the probability that head occurs. Okay, therefore 1 minus P is the probability that tail occurs, right? Okay, so the Bernoulli distribution, and for example, when P, the probability that X is 1 is just P, right? The first try is a head, and then the probability that X is 2 is that the first try is tail and the second try is head, right? It means that in the first try is tail, so that happened with the probability 1 minus P, right? And then the next one is head, it happened with the probability P, right? And similarly, we can write down the probability that Px is 3 is the first two tries are tail and the last one is head. Okay, and you can see the trend here, right? So this is basically a geometric distribution. Okay, so basically this is a geometric distribution, right? So in other words, the probability that X equals to n is nothing but P multiply 1 minus P and minus 1. Okay, so that's basically the probability distribution of X, right? And in this particular case, we know that it's a fair coin, therefore it means that P is half, right? In this case, we can see this guy is half multiply 1 minus half n minus 1, therefore this is nothing but half to the power of n, right? Then this is the probability mass function of X in this case, in this particular problem. Okay, and given that, we could compute the entropy, right? Because the only thing we need to compute the entropy is the PMF, right? In this case, we can compute the entropy using definition. Okay, and then we can write down, so in this case, sum over n, and then we have half n log 1/2 to the power of n, right? And clearly we want to take the log based on 2, right? And then in this case, what we can get is that, so if we move this minus sign inside, we have 2 to the power of n, right? And take the n out, then we just have n, right? Therefore, this is what we have. Okay, so then after that, we can see this summation is this form. We can use that to compute this summation, right? Basically, you can see, so for our summation, n is from 1 till infinity, right? N cannot be 0, but if n is 0, the entire thing is 0. Therefore, we just use that directly, okay? So that's r over 1 minus r squared. So let's write it down. R over r is half, right? And 1 minus r squared. And then we can see that this is nothing but 1 over 4. 1 over 2, 1 squared is 1 over 4. And then 1 over 2 over 1 over 4 is basically 2, right, bits. Right, that's basically the entropy, okay? So let's see the second problem, the part B. Part B is that a random variable x is drawn according to this distribution, and find an efficient sequence of yes/no questions of the form is x contained in the set x, compare hx to the expected number of questions required to determine x. Okay, and at the first glance, maybe you have no clue for this kind of thing, right? So if we don't have any intuition for this type of problem, and so we may ask us what is the most natural thing to do, and try to see how far is that to the optimal point, right, which is the entropy. Okay, so yeah, let's see what is the most natural thing to do here, right? The most natural thing to do here is that so how about we do this, right? So because x starting from 1, right, if it's not 1, then it might be 2. If it's not 2, it might be 3, right? It's like, if we flip this coin, right, in the first try, it's possible to be head and tail. In the second try, it's possible to be head and tail. How about we just, it doesn't make sense to ask x directly from, like, say, is x is 10, right? So I think it makes sense to say is x to be 1 or 2 or 3 and so on. We increase the number here. Okay, let's try that and see how it looks, right? So for part B, so we ask the most natural kind of question, so which is that we say the theories of question can be as follows, right? The first question is that is x equal to 1? Okay, so maybe let's denote the number of questions to be q, right? Let's say q is a random variable, that is the number of questions to be asked, right? So in this case, is x equals to 1 means that its q is 1, right? And then if not, we can ask the second question, is x equal to 2? And this means that if yes, then the number of questions we ask is 2, right? And then the third question is that is x equal to 3, right? Means that q is 3 in this case. Okay, and then go on, right? Finally, so we can compute the total number of questions that we ask, right? So the expected number of questions, which is the expectation of q, right? So that equals to what? Right, so the q should going from 1 to infinity, and it's Q multiply. Now inside would be the probability distribution. Oh, sorry, I didn't. Didn't change it, right? So here. Okay, so this is what I just wrote, right? Is x equals to 1, is x equals to 2, is x equal to 3, and so on, right? So in this case, the total number of questions we asked is basically Q, right? So now we want to compute the expectation of Q, right? That equals to Q multiply the probability that capital Q equals to small q, right? Then this probability is the probability distribution of x, right? So you can see that if q is 1, it means that x is 1. If q is 2, it means that x is 2, and so on, right? So then inside it will be nothing but half multiply to the power of q, right? Okay, so in this case, what we can get is as follows. So basically that equals to q from 1 to infinity. Then we have q multiply half q to the power of q. And in this case, we can see that this is identical as what we used before, which is this one, right? Therefore, so easily we can get this guy is also 2, and then that equals to entropy already. Okay, so this basically means that, so this is the best solution, right? Because the total number of questions we need to ask to resolve x is already equal to the entropy of x, right? So this means that this is the best solution already. Okay, so this is basically the second question, the part B of question 1. Okay, so now let's take a look at our question 2. So in the second question, we let x be a random variable taking a finite number of values, and then what is the general inequality relationship of x, entropy of x and entropy of y, right? And we consider two forms. The first form is y equals to 2 to the power of x, and second form is y equals to cosine x, right? Okay, so let's take a look. So let's go back. So for the second question, so for part A, so what we get is y equals to 2 to the power of x, and so basically in this case we need to compare the PMF between x and y, right? So if they, for example, if x and y have a 1-to-1 mapping, then the entropy will not be changed, right? But if they don't have a 1-to-1 mapping, then the entropy might be changed, right? For example, in this case, we know y equals 2 to the power of x, so this is a monotonically increasing function. Okay, if that is a monotonically increasing function, it means that probability of x equals to x equals to the probability that y equals to 2x, right? And they have 1-to-1 mapping. In this case, we can directly see that the entropy of y will equals to the entropy of x, right? Because when we compute the entropy of y and the entropy of x, the formula, the value of the probability will be identical, right? Because they have 1-to-1 mapping, okay? But for part B, it can be a little bit trickier. So for part B, what we get is y equals to cosine x, okay? And for this function, it's very clear that it is not a 1-to-1 mapping. Okay, so if it's not a 1-to-1 mapping, again, we want to compute the probability of x equals to x and the probability y equals to some other value, right? So in this case, we can see that the probability that y equals to small y, so then we want to represent that with the probability of x and see whether we can compare between the probability of y and probability of x, right? So in this case, we can see that. So maybe if we denote, let's do that. Okay, then this equals to, because it's not a one-to-one mapping, right? It means that for multiple x, we could have the same y, right? In this case, we need to sum over all the x such that y equals to cosine x, right? Does that make sense? Then that is times probability x equals to x, and inside is probability x equal to x, and then we can see this one is clearly bigger than or equal to the probability of x equals to x. Okay, for any x such that x is here. Okay, so in this case, we can compute the entropy of y. That is the sum over y, py log py. Now remember, notation wise, so this is py and this is px, right? Okay, so in this case, we can upper bound this term by the formula that we have seen before, right? Because so this guy which is py is bigger than or equal to any px where x is for y equals to cosine x, right? So in this case, so we can upper bound this term, okay? Yeah, because there's a negative sign, right? Before it's lower bound, now it's upper bound. So that is less than or equal to negative. So we can replace this by the one that we used before, which is sum over x such that y equals to cosine x and p x, and log inside we can replace this by px. Okay, then this equals to, so this is basically sum over all the possible x, right? And we can see here, so this should remind you somehow like a grouping property for the entropy, right? So this equals to this and the log px, and together that will give you the entropy of x. Therefore the conclusion is that this is bigger than entropy of y, which makes sense, right? Because when we do this transformation, y equals cosine x, so the uncertainty of x will be smaller, right? Because we sort of group different value of x to a single y, right? Therefore the uncertainty is kind of smaller, right? So maybe we can recall a little bit for the grouping property of entropy, right? So before, for example, we have this guy, right? P1, P2, P3 is a PMF, right? That equals to, if we combine any two of those, right? And then, so we need to add an additional term, right? Which is P1 plus P2 entropy of P1 over P1 plus P2 and P2 over P1 plus P2, right? And here we can understand this as somehow the form of Px, and this is somehow the form of Py, right? Therefore we have an additional term here, therefore Px will be bigger than or equal to P1. So that is basically the logic behind it, right? The reason is because of this grouping entropy, the grouping property. Okay, very good. So now let's see question 2.3. And for 2.3, it's called the minimum entropy. And this question is that, what is the minimum value of this entropy? We'll consider the entropy as a function of the probability vector p, right? And then ask to find all the possible p that achieve this minimum, right? So let's see how we can solve this problem. So we know that for this entropy is always bigger than or equal to 0, right? And you can see this entropy also equals to negative sum over x px log px, right? And clearly that in this case, each of the term is positive, right? So in order to make this guy equal to 0, so the only possibility is that if and only if each of this, that is 0, okay? In order to make this is 0, and there's only two possibilities, right? So if and only if, or let me write this notation, means if and only if. So P, for example, Px is 1 for some x, and I mean for 1x, right? For 1x, and Px is 0. Maybe let's say Px prime. Px is 1, and then Px prime is 0 if x and x prime are not equal, right? This is the only two possibility, right? So if this is 1, then it's 1 times log 1, which is 0, and if it's 0, and then 0 times log 0 is also 0, okay? And the reason I said only for 1x that's 1, and for the rest is 0, is because that the probability vector summation of the probability vector has to be 1, right? Therefore, it is only possible that only one of them is 1, the rest has to be 0, okay? So therefore, in this case, then we can say that that's it, right? So basically, so what we have here is that the probability vector, all possible probability vector has to be in this form: 1, 0, 0, and so on, or 0, 1, 0, and so on, and so on, right? So there's only one element, so this is a vector P, right? There's only one element that is 1, and the rest elements are 0, okay? So now let's go back and think, right? Here is just from the math point of view, right? But that makes sense. The answer is yes, right? So when the entropy is 0, so it basically means that there's no uncertainty, right? Everything is certain. So everything is certain, meaning that we know x will only equals to one value, right? It is not possible that this x equals to another value, right? This means that, so the probability of x equals to small x is 1, and for the rest, it has to be 0, right? So this basically, this is the answer of this question. Okay, now let's see our next one. The next one is our question number 4. So here it just asks you to explain the meaning of each step here, right? So that should be relatively straightforward. So let's try to explain that. Okay, so 2.4, what we have is hx and gx, where gx is a function of hx, right? So this question, the meaning of this question is to tell you that the function reduces entropy, right? So A is to write this in this form, okay? So this technique is what we use all the time, as you can see, right? So basically what we do here is that we have a joint entropy, and then we're gonna write the joint entropy into two ways, right? And then compare them. Then we can get the result, right? So this is nothing but the chain rule of joint entropy. Okay, part A is because of the chain rule. Okay, and the B is because that, so this is 0, right? Because gx is a function of x. If we know x, then we know gx, right? So the uncertainty is 0. And then we write this in another way, right? Which is hgx plus hx given gx, okay? Therefore, we can see C is nothing but chain rule again, okay? And we can conclude that this guy is bigger than or equal to h g of x, right? The reason of this is D. The reason of this is because that this part is bigger than or equal to 0, okay? And we drop this term, then we can get this guy, right? Okay, all right. Therefore, we can conclude that, so this guy is bigger than this guy, right? hx is bigger than or equal to hgx, okay? And then we're done. All right, so this is our question number 4. Next, let's look at our question number 5. Question 5 is called zero conditional entropy. it is to show that if this conditional entropy is 0, then y is a function of x. Okay? In other words, it means that for all x with the probability of x bigger than 0, there's only one possible value of y with probability of y and yx bigger than 0, right? Let's see how we can solve this question. 2.5, right? So basically what we know is that, so this guy is basically 0, right? And so what we're gonna do here is that we're gonna write a definition of the entropy and see what we can get from the information that this guy is 0, right? So let's write down the definition. So which is this guy, px py given x, right? This is a joint distribution of x and y, and the log py given x, right? And let's say we let this guy equal to 0. Okay, so and from here let's see what we can get, right? So as we said before, so we know, I mean, including this negative sign, every element in the summation is bigger than 0. It's bigger than or equal to 0, right? Therefore, if we want to make sure this guy is 0, the only possibility is that this guy, so each of the term has to be 0, right? If each of the term has to be 0, it means that, so this has to be 0, okay? So because from here, we know that for all x with px is bigger than 0, right? So px, so it could be bigger than 0, right? Therefore, the only possibility is that, so this if and only if each of this guy is 0, right? If this guy is 0, then we can conclude that, so py given x is 1 or 0 given x. Okay, so and we have seen this before, right? Because the summation of this guy, right? So the conditional probability distribution is still a probability distribution, right? So since the summation of this guy is 1, therefore for each x we can find a y prime such that, so this has to equals to 1 if y is y prime and 0 otherwise, right? So this is the same as what we have seen before. Only one possible y has I mean, for this probability point we have a 1. For all the other points we have a 0. Okay, and this, if we want to translate that, this precisely means that, so for a given x, y has to be fixed, right? This means that y is a deterministic function of x, right? That basically, yeah, y is a deterministic function of x, right? This precisely means that. Okay, very good. And now let's see our question number 6. So we have seen this in class before, right? This is a conditional mutual information versus unconditional mutual information, right? Unlike entropy, for entropy we know that conditioning reduces entropy, right? But for the mutual information, it's unclear, right? The condition can either increase the mutual information or it can decrease the mutual information, right? So we have seen the condition for each inequality occurs, right? But we haven't give an example of that, right? But so yeah, let's see the example here, right? The first one is that the conditioning reduces mutual information, right? Okay, so as you recall, so when we discussed in class, the case that the conditioning can reduce the mutual information is when XYZ they form a Markov chain, right? So this is the case where XYZ forms a Markov chain, right? Which means that given Y, X and Z has to be independent, right? statistically independent. Okay, so in this case, so we can have a very simple Markov chain, right? So for example, we can just say x equals to y equals to z, right? That is a Markov chain. It's a very simple Markov chain. And if we compute that, you can see the mutual information between x and y equals to the entropy minus hx given y, okay? And that equals to hx, okay? So yeah, maybe you can pick a special distribution for hx and then to make sure this is not, because this is a bigger one, right? So we don't want this to be 0, okay? For example, we can pick the distribution fx is a Bernoulli distribution with half, right? That means that the probability that x is 1 is half, and the probability that x is 0 is also half, right? In this case, we can compute that this guy is 1, right? 1 bit, basically. Okay, and the other case is that we want to compute the mutual information between x and y given z. So in this case, again, we can compute using the definition of the mutual information, x given z and y, right? So basically, since they're all equal, right? So this is 0 minus 0 equals 0, right? Clearly in this case, this guy is less than this guy, okay? And then we're done. Okay, so this is for part A. And for part B, it is the other way, right? The other way is this guy is bigger than this guy. And as we have seen in class, so what did we do here is that we want to make x and z are independent. So this is only one possibility, right? I think if you make x, y are independent, it also works, right? If x and y are independent, this guy is 0, so I should be able to find a z such that this guy is bigger than 0, right? But here we just follow our class. So in our class, what we covered is that what we said is that x and z are independent, but so they're not independent with y. And in this case, so what we can do is that, so usually this kind of trick will work all the time, right? We just find a simple function, right? If y is not independent with both x and z, so maybe we just write y is a deterministic function of x and z. In other words, y is x plus z, right? So, and here we may assume that x and z are independent. Okay, and then we give them a special distribution. We say it's distributed with Bernoulli again, half, right? That is the simplest distribution that we can use. Okay, so in this case, now let's compute the mutual information of x and y. So this is nothing but hx minus hx given y bigger than 0. This guy is trivial, right? That is just 1. Then we need to compute this guy here. Okay, so in order to compute this guy, we have to compute the conditional distribution and the joint distribution between x and y, right? But because now we know this is a Bernoulli distribution and this is another Bernoulli distribution, then we can easily compute the probability distribution of x and y, right? You can use the convolution property, right? Or you can just compute that brute forcefully, right? For example, here, let's, for example, if you want to compute the conditional distribution x equals to y minus z, right? And then we can compute probability that the conditional distribution we need to compute, like when y is 0, then we need to compute the value of x, right? And let's say the possible value of x here is that, so x, if x is y minus z, right? If y is 0 and if z is 1, then basically x is -1, right? This z is 1. So this will happen with probability half, right? Because y is fixed. And then the probability that z is 1 is half, okay? And similarly, we can compute that probability x is 0, and here is when z is 0 again. So this is a half as well, okay? And similarly, we can compute the probability that of x when y is 1, right? So in this case, we have two cases again. So as x is 0, z is 1, or x is 1, in this case, z is 0, right? Again, the probability half-half. Okay, and with that said, we can compute the probability distribution of x and y because that simply equals to p x given y, compute the multiplied probability of py, right? So we can see in this case, so here is basically all half, right? Here is basically all half again. So together, it is basically 1/4. And you can see that in this case, x and y are basically statistically independent, right? So, I mean, we can just write down all the possible probability here. It's like x is -1, y is 0. Here is x is 0, y is 0, x is 0, y is 1, and x is 1, y is 1 as well, right? And with that said, we can compute easily that. So what do we want to compute? It's an entropy of hx given y. So that is nothing but 0, right? Because that is nothing but because x and y are independent, right? That is nothing but hx, right? Which is basically 1. Okay, and in this case, yeah, because what we want is that this guy is bigger than this guy, right? So what we want is basically this guy is as small as possible, which is the case, right? This guy is nothing but 0. Okay, very good. All right, so this is the one part, and for the other part, which is the neutral information between x and y given z, right? This is relatively straightforward, right? Because that equals to hx given z minus hx given y and z, right? And clearly we know this is 0 because x is a determinate function of y and z, and then this is basically equals to h, and we know x and z are independent, so that equals to x, hx, then this guy is 1, right? Clearly from here we can see that this guy is bigger than this guy. Okay, and then that will be the solution of this question, right? Next, let's take a look at problem 2.7. So this is pretty complex. So coin weighing. So in this case, we have n coins, and among which we may or may not have one counterfeit coin, right? And if there is a counterfeit coin, then it may be either heavier or lighter than the other regular coins, right? And so we weigh all the coins by a balance, right? So in this case, we have two questions. The first one is pretty okay, right? The first one is to find the upper bound of the number of coins n so that k weighings will find the counterfeit coin, right? And correctly to declare it to be heavier or lighter, right? So, okay. And but the second one is to find a specific scheme to achieve it, right? So that is pretty hard. Okay, so let's see the first one, which is the easier case. Okay, so basically the idea to solve this problem is that we need to find, we know that by the by the way, so we have 3 cases every time, right? So it means that we can basically resolve like 3 cases every time. Okay, and we want to see how many cases in total, right? And then we can design a sequence of weighing strategy that we can resolve all the cases. Okay, so yeah, let's write it down. Okay, so first of all, so let's count what is the total number of cases possibly, right? Because we have n coin in total, right? Clearly, one easy case is that all coin are regular, right? There's no counterfeit, right? That is one case, okay? So, and the second case is that so one coin is counterfeit, but is heavier than others, right? So let's say the second possibility is that one of the n coins is heavier, right? If that is the case, then how many possibilities we can have here? So it's n, right? It can be any of this n. So I have n cases here. And the third one is one of the n coins is lighter, right? And similarly, we have n cases in total. Okay, overall, right here, so we have 2n plus 1 cases in total. Okay. So that is all the possibility, all the possible cases, right? So basically, so now what we need to determine is that, so what are the combination, how many number of combinations of this k weighing that we can resolve this 2n plus 1 cases, right? So let's see on balance. Okay, every time there are 3 cases, right? The 3 cases are left, right, which means left is heavier, right? Left, right, and balance, right? So every time we have 3 cases. And with the combination, right, if we weigh 2 times, so how many cases we can resolve? It's 3 squared, right? Because every time there are 3 cases, right? So then this means that if we weigh k times, okay, and there are 3 to the power of k combinations, okay, and in total we have 2n plus 1 cases, right? This means that if we let this guy is less than or equal to this guy, and then we can find an upper bound of n, right? I mean, this guy should be bigger than this, right? So yeah, because that is the total number of cases that we can resolve, right? So this means that n will be less than 3k minus 1 over 2. Okay, so basically that is the upper bound of n if we want to weigh k times. Okay, so that is the one thinking of this solution. And the other thinking is by entropy, right? So maybe you would say this is method 1, right? It's like M1. And our method 2 is that, so we consider that from the information, amount of information point of view, right? We say each way gives how much information, right? Because each way we have 3 cases, right? 3 possibilities, right? Left, right, and balance. Therefore, so each way can give us log 3 bits of information. Okay, right. And so what are the total entropy here, right? We know there are like 2n plus 1 cases, and we don't have any preference for each of the case. We assume they are uniform distribution, right? This means that total entropy means that the total information, right? Total entropy or total information. So that is log 2n plus 1. Okay? And then, so every time we can resolve this amount of bits of information, and in total we have this bits of information. So then, how many times we need, right? It means that k has to be at least this guy over this guy, okay? And so this is nothing but log base 3 2n plus 1, right? And then similarly we can get, in this case, n has to be less than or equal to 3k minus 1 over 2, which is the same as this one, right? So those are 2 possible thinking here, right? But now the question is that whether this is achievable or not, right? We know this kind of makes sense, right, on a high level, but can we design a scheme to achieve it, right? This is part A. Okay, so for part B, that is basically the case, right? In part B, we have 12 coin, and want to try 3 times only to resolve the counterfeit coin if there is one, right? And we can see that, so this should satisfy this formula, right? 3 to the 3 is what? 3 to the 3 is 27, minus 1, 26. 26 over 2 is 13, right? But here we have n is 12, right? So that's less than that. Okay, so in theory, we should be able to find a strategy to achieve it, right? And of course, the strategy is not unique, right? There should be many strategies. And here we just illustrate one possible solution. Feel free to find your own solution for this, right? It's pretty fun. Okay, so let's write one possible solution here. Yeah, this is pretty complex, right? So again, we only have 3 times, right, for trying, and every time kind of like 3 possible possibilities, right? So maybe one intuitive idea is to divide all the coin into 3 groups, right? 3 possibilities. Okay, let's try this. So what we do is that we divide the n equals 12 coins into 3 groups, and weigh any 2 of them. Okay, any 2 of them. Okay, and of course each group have 4 coins, right? So equal partition. Okay, so now we have like the first way, right? And in this case, in total we have 3 cases on the balance, right? The first case is they're balanced, right? The second possibility is that left is heavier, right? Left is heavier. And the third case is that right is heavier, right? Okay, and so for the case that left is heavier and right is heavier, they're pretty similar, right? So we'll just illustrate one solution, I mean the second one, and then we're gonna see the right one similarly, right? Or you can design that similarly. Okay, and so let's see the first one, right? Let's see case 1, right? If they're balanced. Okay, so first case is that if they're balanced, let's see what are the possibilities, right? So if they're balanced, what do we mean by that, right? If they're balanced, so we can conclude that there's no counterfeit coins within these 8 coins, right? There might be one in the third group, or there might not be, right? Because we don't know whether there's a fake, whether there's a counterfeit coin exists ever, right? So from this, the most information we can resolve here is that we can conclude at most we have 1 counterfeit coin in the third group, right? This is the best we can get, right? And also, of course, there's no counterfeit coin in the first and second group that we have weighed, right? And then the question is that what can we do? Okay, so this is the design part, right? So in the third group, okay, so there may or may not be 1 counterfeit, right? So what we try here is that we take 3 of those, right, and then weigh them with the 3 regular ones, right? Because we know for the first and second group, they're all regular, right? So what we do is that then we pick up 3 coins from the third group and weigh them with 3 regular coins. For example, from the first group, right? It's okay to from any group, first or second, okay? And here we say this is our second way, right? Okay, so now let's see what we can get, right? Again, I have 3 cases, right? Because we weigh them, right? So now the 3 cases are balanced, left and right, okay? So let's see the first possibility. Let's say use another index, maybe say case A is that they're balanced again. Okay, so what we can conclude from here? Okay, so if they're balanced again, so what we can conclude is that the left coin, the left coin in the third group may or may not be a counterfeit, right? So because if they're balanced, there will not be a counterfeit coin with these 3, right? So that's an easy case. So this basically means that the left coin in the third group, there's only one left, right? In the third group, may or may not be a counterfeit coin. Okay, so in order to determine that, it'll be easy, right? There's only one coin left. We just weigh this coin with any regular coin, and then we can determine whether it's a fake or not, and whether it's heavier or lighter, right? Therefore, the third way is that we're gonna weigh. So these are the third way, right? So we're gonna weigh it with the regular coin, right? You can from anywhere, right? Because we know there's so many regular coins now with a regular coin, and then we will resolve all the information, right? Then we know whether is a regular or heavier or lighter. Okay, then we can solve the problem, right? So very good. That's pretty easy. So this is the easiest case, right? When they are balanced. Okay, so the hard case is that when they're not balanced, right? So let's say B is that when they are not balanced, right? So in this case, a counterfeit coin among the 3. So we know there's a counter coin among the 3, and so we know it's heavier or lighter, right? Because we have 3 regular and we have 3 counterfeit, right? And if we weigh them, right, if it's not balanced, so we know the counterfeit will be among which 3, right? So we know it's heavier or lighter, right? We can resolve this information, right? In this case, if it's unbalanced, we can say we know there is a counterfeit coin, right, among this 3. Okay, and we know it is heavier or lighter, right? And the only part left is to determine which one it is the counterfeit coin, right? So one way should be enough, right? How to do that? I have only 3 coins. We just weigh any 2 of those, right? That's pretty straightforward to do. So now we just pick randomly two out of the 3 coins, right? And weigh them right? And here is our third way, right? If we weigh this 2 and then we have 3 cases, right? We have 3 cases. And the first case is that they're balanced. And the second case is left or right. So left, right means that left is heavier or right is heavier, right? So if they are balanced, we know the left one is counterfeit. Okay, so because we know the counterfeit is heavier or lighter, right? Therefore, depends on, if it's, we know before it's heavier, then if it's left, then that'll be, the counterfeit, and if it's lighter, then if the right is heavier than the left one, if it's light, and then the left one would be the counterfeit, right? So then we can resolve this case, right? Okay, very good. So this is the overall, that is the first case, right? When the first way is balanced, right? So now we need to take a look at much more complex case, right? Which is case 2. Let's say case 2 is left, okay? So it's left and balanced, right? Which means that is like this, okay? Left is heavier, okay? So in this case, so because they're unbalanced, we're gonna know that we have a counterfeit coin first of all, and then the counterfeit coin would be in either left or right, right? Because we don't know whether it's heavier or lighter, right? So we know the counterfeit coin can be in either groups, right? Left or right, okay? And we also know that the third group is regular, right? So the third group is regular, okay? Very good. So now it's kind of tricky, right? What do we do next, right? So we have some regular coin, and for the first two group, we don't know that, right? So now, so what we're gonna do is that, so we're gonna pick some of the coin from the left group and some of the coin from the right group, and then we weigh them, right? So the way we do that is, so we're gonna partition the coin from all the coins, or pick some of the coins and divide them into two groups, right? The first group is that group A, we have 2 coins. Let's say I have 2 coins from the left group and 1 regular coin from the third group. Okay, 2 from the left and 1 from the third. Okay, and part B, so we're gonna take the other left 2 coins from the first group or from the left group, right? 2 coins or the other 2 coins, right? So the other 2 coins from left group. Remember, the left group is the heavier one, right? And 1 coin. So now it's not from the regular group, right? The 1 coin, that from the third group. Sorry, from the right group. 1 coin from the right group. Okay? So now we weigh them, right? This is the second way. Okay, so this is what we do is that we put A in the left and B on the right, and then weigh them, right? So this is our second way. Okay, and here we can see that. So basically now we mix them together, right? So now let's see the result here. So we have 3 cases. right? The first case is that A equals to B, right? And the second case is that A is heavier than B, and third case is A is lighter than B, right? So we're gonna see this case is one by one. Let's say if A and B are equal, right? What this can tell you, right? Because when we do this, we always weigh something like within the group, right? So if A and B are equal, so this basically means that the counterfeit coin is the left 3 coins in the right group. That makes sense? Right, because we know there must be a counter coin by the first way because they are unbalanced, right? So now if A and B are equal, it means that the counterfeit cannot be in the left group, right? Because we know on the left hand side on the group A is all regular now, okay? And all on the group B, because they are equal weight, so therefore in group B, they're all regular now, right? There's only 3 coins left in the red group, right? In this case, we can know that the counterfeit coin is in the left 3 coins in the right group 8, and because on the left side is all regular, right? Therefore, combine this information second way, we know that the counterfeit is lighter because it has to be here, right? Okay, so we can also get, and it is lighter, okay? So now the only thing left is to find which one of the 3 is a counterfeit, right? Which is pretty straightforward, right? The only thing we need to do is that then we pick any 2 out of 3 from the left 3 coins, right? And weigh them. Okay, so this way is our third way. Okay, and here it's very clear that now I will not write it down, but it's very clear that again we have 3 cases, right? We have balanced, right? If they're balanced, then we know that the left one is a counterfeit, right? And if they're right or left, right, no matter which one is, the latter one is the counterfeit, right? Okay, and then we're done. Okay, great. So this is a case when A and B are equal. The second case is that, let's say, when A is heavier than B, right? This means that it'll look like this, right? Okay, great. In this case, we still don't know where is counterfeit, right? And whether it's heavier or lighter, right? So what can we do, right? So in this case, so what do we know from the left group is that we have a regular coin there, right? And we have other 2 coins from the left, right? So we may weigh these 2 coins from the left group and see what will happen, right? So what we're going to do here is that we're going to weigh the 2 coins from the left group, okay, in A. Right, this way is our third way, okay? So now we can, let's see what can we get here, right? So let's see, we may see one possibility is that one is heavier, right? Either left or right, doesn't matter. If one is heavier, so what can we conclude? Right, if one is heavier, so the heavier one must be the counterfeit and is heavier, okay? So if one is heavier than this one is the counterfeit, and it is heavier. There's no other possibilities, right? Yeah, because now we know it's heavier than a regular one, right? Because, uh, and then from the first one, we know the left one is heavier, right? Combining all this information, we can conclude that so the heavier one must be a counterfeit. Okay, so yeah, this is one possibility, and the other possibility is that they're balanced, right? So if they're balanced, what can we get, right? If these two are balanced, those two must be regular, right? Because third one is also regular, right? So if they're balanced, all the three in the group A must be regular, right? Therefore, the counterfeit has to be in group B, right? And in this case, so we can conclude that because the two from the left group is regular, right? And the counterfeit is in group B, and it has to be lighter, right? If it's lighter and from the first try, right, we know that the left is heavier and the right is lighter, right? With all of this information, so what we can conclude that the only one in the B from the right group has to be counterfeit and is lighter. Okay, kind of tricky, but think this again. So the one of right group is the counterfeit, and it is lighter. Okay, kind of tricky in this case. Okay, so the last case is where A is less than B, right? In this case, so it means that A is lighter than B, something like this, right? Let's see what can we get from here. The counterfeit cannot be lighter, and it has to be in the left group, right? So for example, let's say if the counterfeit is lighter, right, then it has to be here in this group, right? So if it has to be here, then it means that the counterfeit has to be in the left group. So left group is heavier, right? It's a contradiction, right? So the counterfeit cannot be, it means that the counterfeit cannot be lighter, right? And also the counterfeit cannot be, so it means that the counterfeit has to be heavier, right? Therefore, the counterfeit has to be in the left group, right? Again, this is kind of tricky. We need to think about that carefully. Okay, so here, the last try, so what we can do is similar as before. So what we do is that we take the two coins from the left group, but in group B, okay? So now we weigh the two coins from the left group in B. Okay, so this way is our third try. Okay, and in this case, because by doing this, we know it'll be heavier and it'll be in the left group, right? Now there's only one possibility that we have to get one is heavier, right? So one is heavier, right? They cannot be balanced. So in this case, so what we can see is that, so this one is basically the counterfeit. Okay, and it is heavier. Right, so this problem is kind of tricky, but this is only one possible solution, right? So, but now we still have like a case 3, right? But that is similar to case 2, and you can do that on your own, right? And then we finish talking about this problem, right? Next, let's see our next problem. So our next problem is 2.9. So this problem is relatively easier, right? So here, it gives you that it defines that rho xy equals to the entropy x given y and plus entropy of y given x, right? And in this case, you can see that it's symmetric, right? And we're going to show this is kind of like a distance metric, right? Or it's a metric, okay? So basically what we're going to show is that, so automatically that will satisfy the property 1, 2, and 4. And for the third one, we need to define what does this equal mean, right? So if we say that x equals to y if there is a one-to-one function mapping from x to y, right? Then the third equality will hold, okay? So, and then we're gonna verify these identities in part B, okay? So let's try to do this. Okay, so here, let's see. The first one is to show this guy is bigger than 0. So that is pretty straightforward, right? See, the first one is rho equals to rho xy equals to hx given y plus hy given x, right? And then we know each part is bigger than or equal to 0, therefore that is bigger than or equal to 0, right? It's a very simple argument. And for the second one, so it's a commutative property, right? Second one is a commutative property, and you can see rho x y again equals to this guy, right? So what we can do here is, because of the commutative property of addition, right, we can exchange the order of these two. So that gives you, I'll give you this, and by definition that is rho yx. Okay, so that's the second one. And for the fourth one is this triangle inequality, right? Here is xy and yz that is bigger than or equal to xz, and so this can be a little bit trickier, right? Let's see how we can show that. So this is number 4. Okay, so here we have rho xy that again equals to this guy, right? And okay, so here we need to write this rho xy plus rho yz, right? So then that equals to this plus hy given z plus hz given y. Okay, so we can see that our goal is to show rho xy plus rho yz is bigger than rho xz, right? So we need to somehow connect x and z. Okay, there are multiple approaches. Let's see how we can get this, right? So we say this is bigger than or equal to. So what we do is that we connect x and z by conditioning, right? For example, we can do this, right? Then we know, so x and z are connected, right? But in this case, so the reason we can have a larger than or equal to sign is because conditioning reduces entropy. Okay, and then we don't change this part, and then for the next one we don't change, but for the last one we do something similar, right? So we condition here by x, right, in order to connect x and z again. So this may not be the only way to do this, right, but this way will work. Okay, you may try different ways, right? There may not be much intuition of doing this. I just need to try putting x or z somewhere in the conditioning and see if that may work. Okay, so let's see what can we get here. And what's this one, right? Right, so this plus that, this would be nothing but h, x, and y given z. So this is by chain rule, right? Chain rule of conditional entropy. And similarly, for this two, we can also get this is nothing but yz given x. Okay, so now we can get the term of the rho xz, right? Because from here we can get hx given z from the first one, right? And then we can write down the rest as y given xz, and here we can also get hz given x, and then add hy given xz. Okay, and clearly these two guys is bigger than or equal to 0, right? By the definition of the entropy. And then this is bigger than or equal to hx given z plus hz given x, right? And this guy equals to rho icon z. Okay, so this is how we prove the force property. Okay, so now let's look at the second property, right? The third property, right? The third property is by the definition that if, let's say, x to y, so here is a 1-to-1 mapping. Let's say it's a 1-to-1 mapping. Then we would like to show that rho x given y, so this is equal to 0, right? Equal to 0. Yeah, maybe we write this in, okay. So there has to be if and only if, right? Two direction. Okay. Okay, now let's see how we can show that. So maybe we can show one direction here. Okay, let's show this direction first. Let's say if x and y is a 1-to-1 mapping. Here is 1-to-1. Then we can see that rho x y equals to hx given y plus hy given x, right? Because x and y is a 1-to-1 mapping, then it means that if we know y, then we know x, and vice versa, right? Here, clearly, this guy will equal to 0 because both entropy will equal to 0, okay? And let's say if hy given x plus this is rho xy equals to, if this is 0, then we can see that hy given x has to be 0 because each term is bigger than or equal to 0, right? This two term has also be 0, right? So from here, and we can conclude that x and to y has to be a 1-to-1 mapping. Right, by using what we have learned, what we have seen before, right? Because from here we know for the conditional probability py given x, that has to be 1, right, for one term, and for the other term has to be 0, means y is a deterministic function of x, and vice versa, right? So both direction means that x to y is a 1-to-1 mapping. Okay, so this is for part A. Let's see part B. So for part B, we need to verify these identities. Let's see how we can do that. Okay, so maybe we'll start from a new page for part B. So rho x y equals to rho x given y plus y given x. Okay, so for the first identity is hx, hy, and the mutual information between x and y, right? So yeah, in order to do that, so what we're gonna see here is that there are two approaches that we can solve this problem, right? One approach is that we can start from here and to get this formula, or start from this formula to get back to rho xy. Either of them would be fine, right? Maybe the other way is easier, but let's see, we're gonna start from here and see what can we get. Okay, right, so basically what we're going to do now is that so we keep this two parts here, right? We have hxy and hy given x, and we're gonna add some terms here. I mean, this depends on your experience, right? So yeah, because in order to get the mutual information, we need hx, we need hy, and we need these two terms in order to get the mutual information, right? And the other thing is that if we add these two, we may want to minus these two back, right? And the rest is to determine the sign here, right? The sign is basically plus and plus, right? And see, we're gonna see whether it will work or not, right? So what we can do here is that hx plus hy minus hx minus hx given y, and minus hy minus hy given x, right? And then we can get hx plus y minus, so mutual information between x and y and x, right? So that'll be 2 times the mutual information, and we can see that is basically the first term. Okay, and we're done. So this is the first one. So let's mark it. So this is the first formula. Okay, and the second formula is that, so now we're gonna have one mutual information and then somehow have a conditional mutual information, right? Conditional entropy. That is pretty straightforward, right? By the Venn diagram that I've seen before, so it's easily to see that that will hold, right? So basically, let's see. So maybe let's write down this. So yeah, we have 2 ways to see that, right? One from the Venn diagram, right? And the other way is that we can also start from here and see why that will be why that is true, right? Let's see. So in this case, we can see that we have a so let's see. So we may want to combine this guy and this guy here, right? To get a joint entropy, right? And after that, so now let's organize what is the rest, right? And this and that, plus that, minus that, we don't have that anymore. And then what we get is this guy and this guy, right? So we just need to minus hx minus, sorry, so it should be, yeah, here, sorry, it should be this guy, right? So we need to pick this guy here and this guy to make a joint entropy, and then what we left is basically this guy here, right? And then we can see that is hx and y minus mutual information between x and y, and this is the second identity that we want to prove. Okay, and let's see what is the last identity. Last identity is basically this guy, 2 times that minus this minus that. All right, and let's see how we can get that. Okay, and here again we can start from here as well, right? So basically we have 2 joint entropy terms, right? So one is basically that, and then we can combine the other 2, right? So we can get hx plus hy given x, and then add hy plus hx given y, right? And then we have 2 negative terms here, minus hx minus hy. Then we have a 2 times hx and y, because both of them will give you the joint entropy, and then minus hx minus hy. Right, that is basically the last identity that we would like to show. Right, there are a lot of approaches that you can do this, so feel free to use your own approach. Okay, so now let's take a look at our next question. So which is question number 12. Yeah, this question is nothing but computation, right? So here it's given the joint distribution, and then it asks us to compute the entropy, conditional entropy, joint entropy, and the mutual information, right? So this is basically the joint, the mutual information, right? And okay, and let's see how we can do that. Okay, And first, let's write down the joint distribution, right? Which is given by this, right? Okay, let's change our color. Okay, so the joint distribution is given by this table. So this is our pxy, and here we have yx 0, 1, 0, 1, 1/3, 1/3, 0, 1/3. Okay, and because we need to compute the entropy and the conditional entropy, so we need to compute the marginal PMF, right? Let's say for px, what do we get? So px is 0, so that is, right, when x is 0, then we have two cases here, right? So that is 1/3 plus 1/3, that is 2/3. And then px is 1 is 1/3, right? Because this two has to be, the sum of these two has to be 1. And for py, similarly, we can see py equals 0 is 1/3, and the py equals to 1 is 1/3 plus 1/3 is 2/3. Okay, so those are easy. And then next, we need to compute px given y, right? Okay, in this case, so let's see, let's say what is the probability that p, so we have 4 combinations, right? 0, 0, 0, 1, 1, 1, 1, 0. Okay, we need to compute all the possible combinations for this, right? Let's say if both x, so given y equal to 0, right, then x has to be 0, right? Because this is 0, okay? So this is 1, right? And what if y is 0 when x is 1, right? That will be 0, right? Because this is 1. Okay, and the other 4 cases, so let's say what if y is 1, y is 1 and x is 0, right? If y is 1, then x, the probability that x0 is what? Half, right? So 1/3 over 2/3, right? So that's half, therefore that is also half. Okay, so now we have a conditional probability distribution of x given y, and similarly we can compute that for y given x, right? Then in this case we have the possible 4 cases, right? Y equals 1, x is 0, and py 0, x is 1, and y is 1, x is 1, right? And we use the identical approach to compute these 4 items here. So that will give you half, half, and that is 0, that is 1. Okay, and now we have all the probability distribution, right, including the joint distribution, right? Therefore, we can compute all the items there. Right, the first item is the entropy, h of x, right? So h of x is nothing but this guy, right? Therefore, in our case, we only have 2 possibilities, right? That is 2/3 log 2/3 minus 1/3 log 1/3. Okay, so that's the entropy of x. And you can see that y has the identical distribution of x, right? Doesn't matter in this value here, but it's also 1/3 and 2/3. Therefore, hy will be the same as our hx, right? You can double check that. Okay, so next is for part B. Part B is to compute hy given x, right? So here we need to use this formula, y given x, right? Okay, here clearly we have 4 items here, right? So I have 4 combinations of the value of x and y, right? Therefore, we need to see each of those. Okay, so y given x would be this guy, right? We need to use these 4 items here. Half of 0, 1. Okay, so let's see. First one is -3rd log half minus third log half, right? Log half. So the first two is basically given by this two, so it's 0, 0 and 1, 0, right? 0, 0 is 1/3, and 1, 0, y is 1x, and 0 is also 1/3, right? Okay, and similarly for the second two terms is minus third log 1 minus 0 log 0, and this would be 0, this would be 0 as well. Therefore, that equals to this. Okay, and you can double check that hx given y would be the same as hy given x as well. Okay, so now let's see part C. So our part C is to compute the joint entropy, right? That is this one. Okay, and that is pretty straightforward, right? Because we just use a table here. So that is negative 1/3 of 3 terms there, right? Although it's 4 terms, but 1 is 0, right? Because we have a 0 items here. Okay, so we can see that all of them are the same, right? So we use this, multiply 3, then we can get negative log 1/3 or log 3. Maybe that looks better. Okay, all right, so for part D, what we get is to compute this guy minus this guy. And we can see that we know both of them, right? We just need to plug everything in. So hy, we get that here, right? Which is this number, right? So hy is negative 2/3 minus 1/3 log 1/3. And the hy given x is basically this one, right? So minus, or let's say plus 1/3 log half. Yeah, so we can combine this, right? That's 2 log half. Therefore, we just write a 2 here. Okay, and then we're done. All right. So this is basically part D. And for part E is to ask you to compute the mutual information between x and y, which actually can be written as this guy, so which is the same as this, right? Okay, so part E is done. And for part F, the last part, it asks you to draw the Venn diagram of the quantities among those, right? And we have seen that before in class. So basically, what we can draw could be something like that, right? The left circle is hx, for example. Left circle is hy, right? I mean the size doesn't mean anything here, right? So okay, and for this part is hy given x, and this part is y given x, right? Yeah, this is x given y, and the middle part is mutual information between x and y. Okay, and then the whole thing is the joint entropy h, x, and y. Okay, so that's a Venn diagram to represent all the information, right? So that's part F. Okay, so that will be the solution for this question. Okay, very good. So the next one is, let's see, the next one is part 14. So sum, entropy of a sum. Okay, let's see. So in this case, we have two random variables, x and y, respectively, and then let z equals to x plus y, and then we're going to show the following, right? And we see the first part is to show that hz given x equals to hy given x. Argue that if x and y are independent, then hy is less than or equal to hz, and hx is less than or equal to hz. Okay, both of them would be equal to less than hz. If they're independent, that's the addition of independent random variables as uncertainty. Okay, that's pretty interesting. So this can be somehow understood intuitively, right? Because if we do the addition and the x, y are independent, then that is a convolution of the two PMFs, right? If it's convolution of the two PMFs, right, the possibility value we're gonna get will be more, right? Somehow, it adds uncertainty, okay? So it seems intuitive, and let's see how we can solve this problem. It's 2.14, okay? And the first one is to show these two guys are equal, right? Let's see how we can show that. Okay, this is relatively straightforward, okay? So here we can basically write this entropy as z is x plus y, right, given x, okay? And then we can write down definition. So this is, now we only have x and y, right? We just write down x, y, and then the joint distribution between x and y and x, and the log p x plus y given x, right? And we can see that if, so the probability of that will be what? Equals to the probability that p y x, right? Because adding x here, will not change the value of this probability distribution, and similarly here, that will be the same as y given x, right? If we fix x and y, right, this two probability will be identical. Therefore, so we can write this as pyx log py given x, okay? And that is nothing but hy given x, right? Therefore, they're equal, okay? And for the second part, we're gonna prove that this inequality and this inequality will hold, right? So hy will be less than or equal to hz, okay? So this may not have much, when we show this mathematical proof, there may not be much intuition going on here, right? But so, oh, by the way, this is assume x and y are independent, right? Okay, so in this case, we want to use maybe this, what we get before to show that, right? So we know hz given x equals to hy given x, and x and y are independent, therefore this equals to hy, right? And then the only thing we need to show now is that hz is what? Bigger than this, right? Would that be true? It is true, right? So conditioning will reduce entropy, therefore this will be bigger than or equal to that, right? So very easily we can show that. Okay, great. So, and similarly, we can show that hx is also less than hz, okay? That will be identical. Okay, so the second, let's see. Okay, for the second part is that give an example of necessarily dependent random variable in which hx is bigger than hz and hy is bigger than hz. So here, when they are independent, we know this is a direction of the inequality. But now, if they're not independent, right, then we may have the opposite, right? So that is, usually if we add independence among three random variables, usually we make the addition of two will equal the third one, right? But now we have x and y. X and y, they're two random variables, right? So normally what we do is that we can just, make one as a negation for the other one. Y equals to negative x, for example. In this case, z equals to, let's say, for example, x plus y, right? Then that will be 0, right? So this can imply that the entropy of z is 0, okay? Therefore, it doesn't matter. So just let, for example, Bernoulli distribution or whatever distribution, right? To make sure that if x bigger than 0 and y is bigger than 0, we can show that hx is bigger than hz and hy is bigger than hz. Right? One example is that, for example, this should be Bernoulli half, right? Okay, so that is for part B, and let's see part C. But see, under what condition does this guy hold, right? Okay, so hz equals to this plus that. Let's see how we can solve that as well. And what we can know here is that, so we have seen this before, right? For the joint entropy, so that equals to hx plus hy given x, right? So that can equals to hx plus hy, right? When x, y are independent, okay? And we know in general, z equals to x plus y, right? It's a function of h and y. And we know the function will reduce entropy, so that is less than or equal to h, x, and y, okay? And but now what we want to do, make sure is that this equality sign, this inequality sign can be an equality, okay, under what condition? Therefore, so we need to make sure that x and y to z is a 1 to 1 mapping, okay? Then this will become, say, equality, right? If that holds, okay? Therefore, overall, in order to make hz equals to hx plus hy, if xy, let's say, are independent and x, y to z form say 1 to 1 mapping. Those are the conditions, right? Next, let's take a look at question number 15. Okay, so in this question, what we do here is that we have a Markov chain from x1 to xn, and then we want to simplify this mutual information between x1 and x2 to xn to a simplest form, right? Let's see how we can do that. So this is 2.15. We're gonna simplify the mutual information between x1, semicolon, x2 till xn. Okay, so let's see how we can do that. So an important property for Markov chain is that, so for example, given x2 and x1 and all the random variable after x2 will be independent, right? For example, given x2, x1, and x3 will be independent, and given x3, x2, and x4 will be independent, and so on, right? So given that side, so we may use the chain rule, right? Here is a chain rule for mutual information, right? So that equals to x1, x2 plus. So this chain rule looks like the chain rule of the entropy a lot, right? I, x1, and xn given from x2 up to xn minus 1, right? Those are the chain rule. And clearly, by using the Markovian property or Markovity property, we can get this is basically 0 because given x2, x1, and x3 will be independent, and it'll be 0 forever, right? Until the last term. Okay, therefore, this will be basically this guy, and then we're done, right? So that equals to mutual information between x1 and x2, right? So this is question number 15. And let's see, next is our question number 14. It's called bottleneck, right? And we may have, let's say, we suppose that a non-stationary Markov chain starts in one of the n states and neck down to k less than n states, and then fence back to n bigger than k states, and then we have a Markov chain like that, right? So basically, it asks us to show that the middle state where it has lesser possibilities, right? Or less number of states. So that'll be a bottleneck. Okay, and given that, we're going to show there's the mutual information between x1 and x3 will be less than log k, right? Which is the log of the total number of states in the second random variable. Okay, let's try to prove that. 2.16 part A. Okay, so let's see how we can show that. So here, by the data processing inequality, so we can basically show that the mutual information between x1 and x3 would be less than the mutual information between x1 and x2, right? This is the data processing. Inequality, right? And now let's compute this. This equals to x2 minus conditional entropy x2 given x1, right? And because this is bigger than or equal to 0, so that is less than this guy. And for x2, we know x2 at most have k states, right? Therefore, this is less than, using the cardinality bound of the entropy, we have log k here, right? This is the cardinality bound of entropy. Okay, and then we show that this is less than log k. Okay, and next is to ask us to evaluate this mutual information in case 1 and conclude that no dependence can survive such a bottleneck. Okay, so part B, this basically means that mutual information between x1 and x3 is less than or equal to log k, where if k is 1, then we'll have log 1, that is 0, right? This basically means that x1 and x3 are independent, right? Therefore, there's no dependence can survive after, right? If the middle state, there's only one state, right? Okay, great. So this is our question number 16. Okay. So next, let's see the next question. So which is question 19. Okay, so infinite entropy, right? This is just an example that tells you that the value of the entropy can be infinite, even if under a valid PMF. Okay, so this basically tells you that we define A as this formula, and that can be finite, and that is finite. And then the PMF is given by this formula. And then it asks you to compute entropy and show its infinity, right? Okay, so just let's try to compute that. Maybe we'll start a new page. So this is 2.19, and it's just computation, right? We just compute that, compute this formula, Pn log Pn, okay? And yeah, and here we can see that n is from 2, right? So the summation basically is from 2. And then we just plug everything inside. So this is 1 over a n log n squared, and the log 1 over a n log n squared, right? Okay, very good. And next step is that, so instead of log is like a multiplication, right? We can break this into a few terms, right? So we put the negative sign inside the log, right? And then we can write this log as a summation of three terms. So one term is log a, second term is log n, and last term is 2 times log n, right? And then we can break this into 3 terms. The first term is log a over a n log n square, right? And then second term is log n over an log, oh, yeah, sorry. So yeah, n is inside, right? So we need to, right, so, okay, and last term is, okay, an log 2n. Log square n. Okay. Okay, very good. So now let's take a look at some information about A. So A basically equals to this guy. And if we compare this guy and something here, we can see that summation of this guy, right, n log n squared, right, that will be equals to A, right? So basically, the first term can be reduced to log A, right? And we know it's given that A is finite, and we can show that A is bigger than 1. So I mean this guy will be less than infinity, okay, which is very good, and it's finite, right? So it cannot be 0. And for this guy, so we know that it's bigger than 0, right? Okay, and for the second guy, so we're gonna show that this guy will go to infinity basically. Okay, let's see how we can show that. And so yeah, it's not very hard to show that, right? So here we can see we can get rid of the log n term and this square, right? Okay, the only thing we need to show here is that, so A is a constant, doesn't matter. The only thing we need to show that is if we take the summation of this n log n, so we're going to show that goes to infinity, right? So we know from the calculus, we know this is bigger than the integral version of this guy, right? And then we do the integral, and then we can show this equals to what? Just check the integral table. If it's log n, then it will equals to like log x, right? But if it's not log n, then this will equals to something like that, where k is constant, maybe some constant, okay? And then if we evaluate this at 2 and infinity, that all goes to infinity, right? And then therefore we can conclude that this will become infinity. Okay, so that is 19, just computation, right? Tells you that it is possible that the entropy can be infinity. Okay, so next question is our question number 20. So it's called run length coding. So that's basically a source coding approach, right? So the way we do the coding is that, so we're basically gonna count the number of ones and zeros, right? And so if we want to transmit that, then basically we're gonna transmit the R, right? But we also need to tell the R the initial point, whether it's 0 or 1, right? If that is the case, then we can decode X successfully, right? So now the question is to compute this entropy, and this entropy, and show their relationship. Okay, and also bound the differences. Okay, let's see how we can do that. Okay, HR has to be less than or equal to hx1 qxn, right? Because R is a function of the vector of hx, right? And yeah, maybe we can write this as that, right? Okay, and so now we know the relationship between this guy and this guy. And now let's see this guy, right? And here we can see that, so this guy would be equals to this guy, right? Because if we know this and know R, then we will know the original vector of X and vice versa, right? And let's see how we can bound this here. So this is nothing but this guy plus hxi given R, okay? And then we can upper bound it by xi, because we just get rid of the condition, the entropy may increase, right? And now we can bound this, right? There's only one variable, therefore, so let's see whether we have any information for xi. So they're binary random variable, right? If it's binary random variable, then the maximum value here we can get is log 2, right? Which is 1. Okay, so now, yeah, by doing that, we have this will be less than or equal to HR plus 1, and also bigger than HR. Okay, so that will be the result of this question. Okay, so next, let's see next question. So next question will be question number 25, Venn diagram. Okay, so yeah, this question is just purely computation, right? So it defines a three-way mutual information, possibly something like that, right? Which is kind of the same definition when we define the mutual information, but actually this guy is not a mutual information. And here we need to first find xyz such that this guy is less than 0, right? And then we need to prove the following two identities, right? Okay, let's see how we can do that. Let's say 2.25. So the first question is to show this guy u and z that is less than 0, right? Which is equivalent to show that it's less than, right? So you should be familiar with that, right? So you should, because we have seen that before. Okay, so let's recall. So we have this homework question before, right? So what we do is that we can let x and z independent, and then let y equals to x plus z, or z equals to x plus y. Yeah, y equal to x plus z. Okay, yeah, we can double check. I think that should be the case. So when did we cover that? Should be pretty fraught. It should be, oh, pause it. Should be here. Okay, it should be part B. Yeah, here, right? So we let y equal to x plus z, and x, z are independent, right? So that will solve the problem. Okay, very good. Let's go back. There an easier way to go back? Okay. Okay. Okay, great. Yeah, why it's not moving? Okay. Okay, great. Okay, so that is the case. And then next we need to show an identity, right? Which is basically this identity. Okay, so let's see how we can do that. Okay, part A is to show an identity. So we need to write down the definition of this first. Yeah, here, we just try to manipulate this, until we arrive that term, or vice versa, right? So we can also start from here and then arrive here. Okay, both of them will work, right? That depends on your preference. So here we can see this guy equals to the mutual information between x and y minus that, right? And we also have a mutual information between x and y here. So it means that we may not want to change this term, right? So therefore, the question reduces to show this conditional mutual information equals to the rest here, right? Okay, so let's see how we can do that. So basically, yeah, we just do this step by step here, right? So we can see that we have an xz here, right? And is there a way that we can get the mutual information between x and z from here, right? Yes, we can, right? Just use the chain rule of the mutual information, and then we can get the mutual information between x and z. Okay, so that is nothing but the mutual information between x and yz minus the mutual information between x and z. Then we get this term here, right? So which is x and z, and we have plus, which is identical, right? And then let's see what we can, maybe we write one more step here to make it look better, minus mutual information between x and yz here. Okay, so the next step is that you can see we have lots of this entropy term here, right? But is there a way we can write this as that kind of entropy term, right? We can, right? Okay, so basically for this, we can use the kind of the Venn diagram, right? Or the definition of the mutual information. We can basically write this as entropy of x plus entropy of yz minus the entropy of x, y, z. So yeah, that is like the Venn diagram, like hx add hy minus hxy equals to mutual information. Okay, and given that, let's see what we can get, right? Let's write one more step here. xz, okay, and here we have one entropy term x, and we have one entropy term x and yz. Right? Those should be the term that we need here, right? We need x, we need x, y, z, right? But we don't need the entropy of yz here, right? But what do we need is another mutual information between yz and the entropy of y and the entropy of z, right? Clearly, we just write this as, let's say, minus as, because we know the mutual information equals to entropy x plus entropy z minus entropy yz, right? We can manipulate that to get this term as entropy y plus entropy z minus mutual information between y and z. Okay, so then that is basically the solution, right? We're done. Okay, that's it. So if you compare this and that, it's identical. Okay, and for part B, it's very straightforward. Okay, you can see that for B, we do not have any mutual information anymore, right? So therefore, the only thing we need to do here is to write down the definition of all of this mutual information, and then we're done. Okay, so part B, we just use the mutual information between this as hx add this minus z. Okay, and also yz equals to the same thing, and xz equals to similar stuff, and then we're done, right? Okay, great. That is for question number 25. Now let's take a look at our last question, which is question number 29. So in this question, again, we're going to show these inequalities, right? Let's see how we can show that. So this approach is very similar to what we have illustrated in class, right? So let's see how we can show that. Okay, 29. Okay, so the first one, part A, we need to show this guy is bigger than this guy, and of course we need to also show the condition where the equality sign will hold. Okay, and this is pretty straightforward, right? It's like the joint entropy, of course, is bigger than, just entropy, right? Okay, so this is a conditional version of that, right? So that is straightforward. So the only thing we need to do is to use the chain rule to write this as a summation of two parts, right? And we know this guy is bigger than or equal to 0. Therefore, overall, this is bigger than or equal to that, and we're done, right? And we see the equality will holds if and only if this guy is 0, right? When this guy is 0, right, is y is a, maybe, let's say, let's one more step here. So this is 0. So this means that y is a function of, maybe that the same thing, right? Or a function of x and z. Okay, and then we're done. For the second part, we need to show, so this mutual information is bigger than this mutual information. Okay, so this can be very similar, right? Just use the chain rule of the mutual information, because the mutual information is also bigger than or equal to 0. The mutual information between y, z given x, right? And clearly here, this is bigger than 0. Therefore, we have this is bigger than or equal to this guy, right? And again, here, the equality will hold if and only if the mutual information this equals 0. This basically means that given x, y, and z are independent, are are maybe, let's say, a conditionally independent. Okay, very good. And next, let's see part C. Part C is to show this is less than this. Okay, let's see how we can do that. For part C, so let's start from the right hand side. Okay, so let's see. So what we want to show here is that we want to show this is xz and x, right? We want to get rid of the y here. Okay, so let's see how we can get rid of the y. Okay, so basically, since we want to get rid of the y, right? So then, and also want to get this xz and x out, right? So let's just do that. Basically, we want to get xz out, and then by the chain rule, we get this, okay? And for second, we want to get x out, and then have that, all right? And then this is that we have xz minus hx, and this is what we want, right? And let's check out what we left here. So this is hy given x and z minus hy given x, right? Okay, and what is that? Right, this is basically minus the mutual information between y and z given x, right? Therefore, we have this given x, okay? And clearly this is bigger than or equal to 0, right? Therefore, we say this is less than or equal to x and z minus hx, okay? And the equality sign will hold if and only if this guy is 0, okay? So the equality sign will hold if and only if this mutual information is 0, right? So basically, this means that given x, y, and z are conditionally independent, which is identical as the condition we have seen before in part B, right? Yes. Okay, so next, let's see the last one. Last one is to show this guy is bigger than or equal to, this guy, right? Let's see how we can do that. For part D, is the mutual information between x and z given y, right? So let's see. So x and z given y, and what we want to get here is that we have a mutual information between z and y given x, and mutual information between z and y, and also mutual information between x and z. Okay, how can we do that, right? Usually we use the chain rule, right? It means that, so we can see clearly there's a relationship between this guy and this guy, right? Because this, if we add this and that, so we may be able to get a mutual information and another mutual information term, right? So let's try to do that. So this basically equals to mutual information between y and z minus mutual information between z and y. Okay. Okay. So now let's see, we have z and y here, and then we need this term, somehow this term and this term, right? So this is the mutual information, so we just need to expand it in another way, right? This is one way, so let's do that in another way, which is not x and z, so we need to do that. So before, let's see, before do this in the zy, right? Zy, now let's do this x and z first, right? And add zy given x, and then minus this, okay? And if we compare this and that, we're gonna see they're the same, right? Therefore, it's always an equality. It's not an inequality. Okay? All right, and with that said, so we finish going over all the homework problems. And so please try to think that again, right? If you haven't, about every problem carefully and see whether the solution makes sense or not. All right? So please let me know if you have any questions or comments. Please stay safe and healthy. Otherwise, I'll see you next time. See you. Bye.